Perfect. So now that we, I hope you can hear me well, because I'm still at the airport. Now that basically, still, I mean, again, now that I kind of connected all those dots about the VQE, I want to refresh quickly what the difference was, which was the difference between that and QAOA, because let me just, I know I've done this already, so I just wanted to go through this again once more quickly, and see how do they go about measuring the expectation value, if that's happening at all. Um, so basically, this answers as a VQA as an algorithm for solving approximately a special class of problems, namely combinatorial problems, and VQA is a possible subroutine to QAOA, but not necessarily as in the case of MaxCat. Let me explain. This solves the problem of an approximate the smallest eigenvalue of some Hermitian operator H, which we usually just call Hamiltonian. As a byproduct, we also obtain a classical description of the approximate ground state, thus basically varying over efficiently preparable ansatz states, and the quantum subroutine determines the expectation value. So there is an expectation value calculation as well in QAOA, right? Ah no, that's VQE, sorry. By a sampling procedure. Okay, in QAOA, your cost function, or Hamiltonian, is given by this, where this term are operators diagonal in the computational basis. Importantly, the eigenbasis of H is thus the computational basis, and one of the computational eigenstates encodes the solution of the problem. This is not the case in VQE, so how does QAO proceed? What? So your cost function is given by these, where these are operators diagonal, or the C, I, Z are operators diagonal on the computational basis. I don't quite get that. Importantly, the eigenbasis of H is thus the computational basis, and one of the computational eigenstates. Okay, so it's basically saying. Okay, so it's basically saying that your observable, or the stuff your observable, or the thing you're trying to measure, you just express it in terms of your computational basis. So you don't have to calculate the expectation value. That's what it's saying, because it's already your computational basis. So it's already your. Okay, so you're expressing it in terms of your computational basis. This is not the case. So how does QA proceed? On high level, without going into many details, in a similar way. So optimize over variational parameters in some ansatz state. This state is called this in QAOA, and it ought to maximize the expectation value. And this step, VQ, can be used as a subroutine, as is especially the task if you can achieve finding good parameters, but it might not be necessary. In the original QA paper, the authors argued that for the particular instance of MaxCat, an efficient classical equation exists, blah 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 blah. Here we necessarily go quantum. Here we need a quantum device. Prepare the optimized ansatz over and over again. The state should have a large overlap with the eigenstate to the smallest eigenvalue. How is QAO approximate, you might ask now? Well, how much computational resources are willing to? So the is approximate in the sense that it tries to find a trade-off in the optimization procedure. Okay. Okay, but it doesn't explain. So it's basically the same, but what you're saying is that the Hamiltonian is expressed in terms of the computational basis. That's it. I might have to really dig into the actual QAA paper again. I've never done it, I think. Okay, ansatz. An introduction to, I think that's the one that I have been taking a look at before, because I want to go back to that eventually, but I just wanted to try to quickly make sure if I can use those connecting dots to just figure these things out. The Wi-Fi is slow at the airport, so discuss workflow, applying MaxCat, problem statement development for QAOA. Specifically, the shadow complexity problem depends on P rather than N. So basically some of the explanation might be trivial to readers. That suppose we wish to maximize an objective function, where z then is a function that queries string z to see if the substring satisfies a certain property. Yeah. There are 2 to the power of n possible different z's, and classically we have to query each of the z inquiries. It's still unclear how to solve this problem exactly efficiently. If an approximate solution is all we need, then we're already classical. Okay. I was going through this recently again. I don't remember when. What's going to say a vector with basis? We can construct arbitrary state as general superposition, where AZ are. Is this to check that it corresponds to basis state for? I'm not following. I think that needs too much detail right now. So it's only in other words, we can maximize and obtain some max, then it means that we're applying z, which means if we measure a state phi with z basis, we will obtain z prime with probability 1. Can only find phi that is a superposition of z basis and with the probability for obtaining z. Okay. What is the continuous variable? So it was Jack Serrani. Let's see if he quantum computing. I don't know. So Dutch algorithms. Is this his latest? No, that's Quora. Okay, no. Plus and improved. Oh, this is the one blog post. That one I'm looking for. He encodes that in the position, but there's no expectation value calculation here, right? I mean, because you're measuring exactly what you're encoding. Expect. No. No. There's no. There's no. But that's because if you're using one particular observable, and that's probably enough in that sense. The thing is, what you're trying to measure this energy thing. Because here it's a convention, whatever you use, right? So I'm assuming then it doesn't matter. But then here, this means the content we added the front set condition. This can be easily controlled. Controlled rotations. So basically, because what it seems to me is the recipe here is basically you're using rotations, like Z rotations. So you're encoding it. So the type of answers you're using is that's 2 components. The first one is what they call the cost function, and the second one is like the mixer they talk about, or Jack and other people talk about. So and the idea here is you're just using the first component is just the recipe of rotating basically around the z-axis, and that's why if you have that combination of these and then a mixer, you're just measuring. So the idea here is you don't need the expectation value because what you're observing is already the observable is already what you're using by convention. So I think that's the idea. It's really the same as I'm saying here. These announcements. Give me a second. You're basically here using the position observable. That's why you don't need to do any expectation value calculation, because you're measuring that already. And I assume this is the same here. So you're encoding your problem in your computational basis. But then what is the mixer for? So phase change alone does not change the probability. Exactly. Phase change alone does not change the probability of taking a certain basis, since it's just rotation. So we have to introduce rotation operator. Here define B. We define this, that the composition of B is exact because a rotation operator. Okay, so it's just a rotation just to make the probabilities change. That's it. And you can parameterize that as well. It's not guaranteed that after the application of the cost function in the mixer, the new state is good enough. So it's applying multiple times. Okay, yeah. So that's why it's not. So the steps begin with the trial state, initialize parameters, construct this, measure this in the computational basis, set and obtain a value z, calculate your cost function. Yeah, that's it. Then it's basic. So that's why. That's actually that specific case where you're using basically by definition the basis you're already computing in. So you're not here. You don't need to deal with. So VQE in general is like the general recipe. That's like minor observable because whatever you're trying to observe, you need to be able to express that in terms of your computational basis. Otherwise, and the way you do that is by calculating the expectation value, because when you're. But I'm curious if here you also it just says measure, right? It doesn't say calculate the expectation value. It just says measure, calculate the value. I wonder whether. Ah no, you see exactly. So repeat step 1 to 4 to a number of times. It means we measure the same for many times and to obtain distribution of states. Each corresponds which with largest value and ever. Each z corresponds to a cost function, okay, which results in a distribution of z's with largest value prima. An average expectation value of c will be, and this expectation value we only output. And its eigenvector as the result of applying to P. Yeah, but again, that's then trivial in the sense that that's just calculating the average of your measurements over your measurements because you're already on your computational basis. Exactly. Good. I think now I get it. Now I get it. It kind of makes sense. It kind of makes sense. So it's the same thing. But basically with VQ it's the more general thing, which is like, hey, if you're willing to measure the energy, then you're gonna have to do that calculation where you express your observable in terms of your computational basis. Yeah. But wait a second. Oh man, these announcements are so loud here. I hope you can hear me well, because I think the microphone should work well. But what I'm reading here is basically that in the QAOA we actually only output the largest value of the distribution, not the expectation value. That's interesting. That's definitely interesting. I'll ask that in Twitter. That's interesting. Just the largest value? Why would you do that? I guess you can do whatever you want, but why would you do that? Then you're playing the max cut problem. Blah, 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 blah. Simplifies computation, preventing traverse Isaac model. And then you have the mixer at the end. But the final state, the first term on the right can be calculated directly based on the distribution of Z bases, since final state is an eigenstate of the Z matrices. So but you still, because you're in the Z observable, you still gotta replace your measurements by the eigenvalues because that's what your measurement apparatus is actually measuring, the 1 and the minus 1, not the 0 or the 1. Yeah. The power. So here we've got like an x. Okay, in terms of x, to measure the result with a change of basis from z to x to applying a Hadamard gate. Before. Okay, so at the end you're actually doing that as well. I mean. I mean, to do the mixer, then it looks like you really have to do that as well. Then it's just the same. An example of post-processing of H of this is given in Appendix A4. So, but I don't quite get it. So you're still measuring the whole circuit in the Z basis, and then the whole circuit in the X. So you're doing this on the Z. You're measuring the Z observable and the X observable. Why? Because that's how your Hamiltonian is built, I guess so. Yeah, but that's the same. Then it's kind of the same principle. It's literally the same principle. It's just VQ is extremely generic, and QAO is just telling you to use the Z and the X to mixer. But here, mix a Hamiltonian. But here they're just measuring once. You know, they are just measuring one observable. They are not like they're measuring the position. That's it. After all is left to do is measure our mode with the next homodynamic measurement. Wouldn't you have to do something here based on the mixer? Non-commuting mixer. Spain the Hamiltonians are applied repeatedly to the initial state one after the other for a fixed number of steps we call P. This means that we define evolution or revolution. Indexes, constant parameters. Since the cosmetic corresponds to a function that we're trying to optimize, we can write it in the form of a function we're attempting to optimize. But in terms of the x quadrature, as this is the parameter we're optimizing and measuring, this means that we have, yeah. Okay. Number Hamiltonian. We will use one of the examples provided in the paper, the number Hamiltonian, which is the format where n is the number of modes in a circuit, and we have to consider now that we'll implement these unit trays in a quantum circuit. Well, okay. Function that we're going to really call based on P. So this is what I don't kind of get. Oh, come on. So, traverse Isaac model. For an aligned on the interaction speed, the Hamiltonian for TFIM is the following. Okay, but this is a bit different, and it's so loud. Finally, stopping with these STEM announcements. Is that a oh, come on. The normal workflow will be the same as in the previous chapter. However, some more simplifications can be performed based on the property of graphs. First, it is p steps because it contains terms that mixed one more outer layer of qubits each step. This is a powerful step because now complexity is transformed from n dependent to p dependent. So if p is fixed on, okay, whatever. We ask all remaining passengers to proceed to gate D3 immediately. But this thing with the Ising model, that's not clear to me. Because there's an X observable in here. So at last term of the first summation, and as described before, we can implement this in QAOA with C, the cost function equals the following Hamiltonian. For B, we still have the term X, the same X properties as before. Notice that we can simplify the expression before. Okay, so we'll consider the result processing contains two parts. Yeah, but okay, these I kind of don't quite understand. The result processing contains two parts, this and this, where the final state equals this. The first term on the right can be calculated directly based on the distribution of Z basis, since final state is an eigenstate of Z matrices. The second term requires more work since phi is not an eigenstate of expectation value of this, expectation value of this. Okay, but that's expressed all in terms of the Z. I don't understand that. We made a mistake. Huh? In order to get the second term, we have to measure the result with the change of basis from Z to X by applying Hadamard gates before measurement as shown below. An example of post-processing of H for a 2-qubit system is given in Appendix A4. Okay. And so for H2 is this. Okay. Yeah, but it's essentially the same. It's really the same. I mean, it just has that very specific approach. But the concept is the same. So we've got the observables that you got to be careful, because whatever you're trying to measure, so if you try to then construct what's your observable, right? Like whatever you got to measure, you got to decompose that and understand how this is built up from the native observables in your quantum computer. So that's the most important part. Perfect. Yeah, I think that was maybe not super needed, but I just wanted to kind of go quickly through that, and I realized that really the QAOA is just the same. It just has that, basically the recipe that says just use the set observable, just use the computational basis to encode your problem, and then add the mixer layer, because then that's what really changes your probabilities. Yeah. But I mean, even that, you need to understand what you're measuring, and I think even with that layer, you don't even need to you might not have to actually measure two separate things like we're doing here with traverse Ising model. I don't understand that. Do you really need to? I thought that was just to mix the stuff, right? That's why it's called a mixer, just to make the probabilities change. So basically, that's just a layer to make those changes in here happen. Plus, in the VQE tutorial from Google, from Circ, that's the Z observable, not the X observable. That's kind of what bothers me the most as well. So I think you don't really need to do that. This is just, I don't know if this is correct in here. I really don't know if this is correct. But I know the Roth idea at intuition level. I think the mixer, this is just to make the probabilities change based on your phase changes you've done here. That's it. Whether you gotta do some basis change or not, whether you gotta do some base changes or not, that's another story. That's a completely different story. That depends on your Hamiltonian, and that depends on the observable you're trying to observe. That's it. No, it's fine. I'll just put that aside. I'm at the intuition level. I think that's the concept. It's the same.